Alright, so today we're starting chapter 9, which is all about right triangles. And we'll get into some right triangle trigonometry stuff before the chapter's over. Starting off, we're looking at something called a geometric mean. Right, so geometric mean of two positive numbers, a and b, is the positive number x, such that a divided by x is equal to x divided by b. So if you solve the proportion for x, you find that x is equal to the square root of a times b. Right? So if we work that out as a proportion, a over x equals x over b. Then you cross multiply, you get x squared equals ab, and to solve for x, then you take the square root of both sides, right? So x is equal to the square root of ab is what it's saying right here. All right, so theorem 9.1 says if the altitude is drawn from the hypotenuse of a right triangle, remember an altitude goes from a vertex to the opposite side, or the line that would be an extension of the opposite side, and it intersects it at a right angle. Okay, so if we got an altitude drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and each other. All right, so I have this altitude drawn right here, which divides this one big right triangle into two smaller right triangles. And in this case, all three right triangles are going to be similar to each other. Right, so all the angles are the exact same, and the sides are proportional to each other within all three of them. Right, so just like we did all the proportional stuff and similar polygons in the last chapter, it's just kind of an extension of that. So then theorem 9.2, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the lengths of the two segments. So the altitude, so from C to D here, is the geometric mean of these two parts of the hypotenuse that the altitude divides the hypotenuse into. Right, so BD, the length of this part of the hypotenuse over the length of CD, the altitude, is equal to the altitude CD divided by the length of AD. Right, so that geometric mean, remember, basically in a proportion, it means it's on the bottom on one side and the top on the other. Right. And theorem 9.3, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. All right, so still looking at an altitude dividing a hypotenuse, but it says the length of each leg of the right triangle is a geometric mean. So CA is a geometric mean of the length of the hypotenuse and the segment of the hypotenuse that's adjacent to the leg. So you take the whole hypotenuse, AB, and the part of the hypotenuse, AD, that is adjacent to CA. If you're looking at CB, it's a geometric mean with the whole hypotenuse AB and the part of the hypotenuse that's attached to CB, which is DB. Right, so CA will go on the top and bottom with AB and AD. CB we go on the top and bottom with the whole hypotenuse AB and DB. Right? So this altitude's like a dividing line. Right? So it's the whole hypotenuse and the part that's on the same side of that dividing line as the leg that we're looking at. Sure, this is kind of confusing. It'll make more sense once we start working out the problems. Questions so far? All right, so we got triangle ABC, altitude BD, and we want to identify the similar triangles in the diagram, which I've gone ahead and taken this image here and broken it up into triangles representative of what's actually in this picture. So you got the original triangle ABC with the 7.8, 12.3, and 14.6 for the sides. All right, the altitude divides that triangle into two smaller triangles. You got this triangle here, triangle BDC, so I've just drawn it right here. So 12.3, 12.3, so it's the hypotenuse of BDC. The H is the length of the altitude, and DC we don't have an exact measurement for right now because we just know that this whole side of the side AC is 14.6. And then you got the smaller triangle, triangle ADB, which is still similar to the original triangle, just smaller. Right? And so its hypotenuse is the 7.8 that we see over on this side of ABC. Right? So these three just represent all the triangles in this image, just so you can see them a little clearer. Which, when we work out some of these problems, it sometimes is easier to go ahead and redraw the three triangles so you can see them separately instead of trying to see them all fitting into the same image there. So we want to identify the similar triangles in the diagram. So we've got triangle ABC, which is similar to triangle BDC, which is similar to triangle ADB. Plus, when we draw them out like this and we have them all in the same representation as far as the way they're sitting, it's a little easier to see how those letters compare to each other. Alright, so then we want to find the length of H. So H here, or H here, or H right here. It's all the same length, just in different triangles. And so since these are all similar triangles, then we can use a proportion just like we used in the last chapter to solve for that. So we look at this triangle compared to this triangle. H and 7.8 go together, and then we've got 12.3 and 14.6 that go together, right? So we can build a proportion with those values. So we'll look at H over 7.8. That should equal 12.3 over 14.6. And then it's just a proportion, and we solve it just like we have all the other proportions in the past. So cross multiply, give us 14.6 times H is equal to 7.8 times 12.3, which is 95.94. And to solve for the H, divide by the 14.6. Which is not going to come out perfectly even, so I want to say H is approximately, because I'm rounding here, 6.57. And the thing about it, if we wanted we could have used the small triangle comparing to the big triangle. We would have done the 7.8 here over 14.6 and the h over 12.3. But either way, we come up with the same answer for h. It'll work out the same. All right, so once again, another example kind of like that last one. We got a right triangle with an altitude going to the hypotenuse, which is going to divide this one right triangle into two other triangles. And I've redrawn them all out here so you can see them in the same representation. And so we want to find h. So we've got all three sides for the big triangle, 6.3, 3.1, 5.5. And we can use the h in either one of these triangles, the mid-size, the little one, either one, to solve for h. I'm just going to use the little one because we used the mid-size one earlier. So the h of yw on the little one is going to go with the 5.5 in the big triangle. And that's going to go along with 3.1 in the small triangle over 6.3 for the bigger triangle. So you can cross multiply those. You go 6.3 times h equals 5.5 times 3.1. Be 17.05. Divide both sides by the 6.3. And when we do that, h is going to be approximately 2.7. So just using the same properties of similarity that we learned in the last chapter to solve for the altitude here. All right, so now we're going to look at the other possibilities for these kind of problems. And if we look back at our theorems here, we know then a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the lengths of the two segments. So the altitude and the two parts of the hypotenuse can be used in one proportion. So that's what we're going to be doing with these next couple here. All right, we've got an altitude, and we've got the two parts of the hypotenuse that it's divided into. The altitude is the geometric mean. All right, so when it tells us that something is a geometric mean, that means that we can start building our proportion, and that value that it says is the geometric mean goes on the bottom on one side and the top on the other. All right, so you can start building your proportion. It says this is the geometric mean, and I'm going to put it on the bottom on one side of the equal sign, top on the other. All right. And then from there, I can put the two parts of the hypotenuse, right, 6 and 3, in the other two spots. So really, it doesn't matter which one goes in which spot, because when we cross multiply, we're multiplying those two together. All right, so if we cross multiply, it's going to give us x squared equals 18. And then take the square root of both sides. So x is equal to the square root of 18, which wouldn't come out perfectly even because 16 has a square root and 25 does, but so it's somewhere between 4 and 5, right? But we can simplify the radical. If you remember how to do that, right, we can take that number underneath the radical, kind of do a factor tree of it, which 18 is 2 times 9, and 9 is 3 times 3, right? So anytime you have a factor tree, anything you have a pair of would come outside the radical. Anything that's by itself stays under. So ultimately we could say x is equal to 3 square roots of 2, right? We had a pair of 3s, so 3 comes out. The 2 all by itself, it stays home underneath it. All right, so this one had a altitude with the 2 parts of the hypotenuse. This time we don't have an altitude, we have a leg, right? Which takes us back to theorem 9.3. Right? In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The length of each leg of the right triangle is a geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So the leg is the geometric mean. Alright, so the leg, being the y, is our geometric mean. So build our proportion, and y goes on the bottom on one side, top on the other. And then from there, it's the geometric mean with the hypotenuse. So that's the whole length of this side, right? Which is 2 plus 5, or 7. So 7 is one of those terms. And the other term is the length of the segment attached to that leg. So our hypotenuse is divided into 2 segments, 2 and 5. And we use the one that is adjacent to the leg that we're looking at. So y is the leg we're looking at, 2 is the side that is, or the segment that's attached to it. So 2 is the other number that goes in there. So we can cross multiply, and we're going to get y squared equals 14. Take square root. Y equals the square root of 14. If we were to do a factor tree on 14, you just get 2 and 7, and both of those are primes, so we just leave it as y equals the square root of 14, which is a little more exact than if we plug it into a calculator and have to do some rounding on the answer. Questions there so far, anybody? All right. So this next bit is just a little bit more of the same, some of them a little bit more difficult than those examples. So here we have an altitude dividing the right triangle. They gave us a leg here, 7. We don't have an altitude value, so to solve for the x, we're going to use the leg as our geometric mean. So 7 on the top, 7 on the bottom. Just to show you that, like before, I put it on the bottom on the left, top on the right. It doesn't really matter as long as it's on the top on one side, bottom on the other. All right, and then it's the geometric mean with the whole hypotenuse, which the whole hypotenuse here is 4 plus x, right? Those 2 parts added together. So 4 plus x goes in one of those spots, and then the part that's attached to the leg, which is 4, goes in the other one. Cross multiply, and we're going to have 49 is equal to 4 times 4 plus x, making sure that we distribute that 4 times that whole quantity, 4 plus x. So 49 equals 16 plus 4x. Subtract 16 from both sides. We get 33 equals 4x. And divide by 4. And 33 divided by 4 is 8.25. Don't have to round that one because it actually comes out at exactly 8.25. Questions on that one? All right. So then this next one is back to them giving us an altitude. We don't have any of the either one of the legs here. So we got the altitude, which goes with the 2 parts of the hypotenuse, which this part we don't have a value for. But we know that the whole hypotenuse is x. This part is 8. So what's left of this part would be represented as what? Anybody? Whatever the whole hypotenuse is minus the part over there at the other side, which is so x minus 8. So now we've got a value to plug in for each part of the hypotenuse. The altitude is the geometric mean. So start our proportion. And the altitude goes on top on one side, bottom on the other. So 14 and 14. And then the 2 parts of the hypotenuse fill in the other parts. So 8 and x minus 8. Cross multiply to solve it. So we have 8 times x minus 8. And 14 times 14. I believe is 196. Right. We distribute the 8. It'll give us 8x minus 64 equals 196. And we're adding 64 to both sides. So 8x equals 260. And last step, divide by 8. And our x value is 260 divided by 8, which is 32.5. Then next up we've got one a little more complicated because it's got a square root sitting in there. And so that square root is on the altitude. And so when we're looking at the altitude, we've got to go with the 2 parts of the hypotenuse. We have this part is 12. And so this part right here would be the whole hypotenuse minus the 12. So x minus 12. And so the altitude goes as the geometric mean, 4 square roots of 7 on the top on one side, 4 square roots of 7 on the bottom on the other. And then 12 and x minus 12, fill in the other two spots. And we're going to cross multiply. And when we do, when we multiply terms with radicals in them, things under the radicals can multiply times each other. Things outside the radicals multiply times each other. So 4 times 4 is 16. And square root of 7, square root of 7. If you know how to do these, you know that that just cancels out the radical. But if you didn't recognize that, then 7 times 7 is 49, right? So 16 square root of 49 is going to equal 12 times x minus 12, which distribute the 12 and take the square root of 49, so that gives us 16 times 7 equals 12x minus 144. Sixteen times 7 will be 112 equals 12x minus 144. And solve for the x now. We add the 144 to both sides. So 256 equals 12x. Divide both sides by 12. And 256 divided by 12 will give us 21.333333. Or put the little repeating bar over the 3. So 21.33 repeating equals our x value. Right. Questions?